Let's just review a little bit before we go on. Remember, we're dealing with hundreds, which is 1 times 100, the tens place, the units place. Then we have the decimal point, where we're dealing with tenths, and that represents numerically 4 times a tenth, hundredths, 5 times 1/100th, and thousandths, and this number represents 6 times 1/1000th. Again, you need to keep in mind that the decimal point is the dividing point between numbers that are greater than 1 and numbers that are less than 1. Now let's look at the addition process, and we're going to start from basic principles and wind up with a very simple result. Let's look at adding these things and pretend we don't know anything about adding decimals. Remember, we have looked, though, in the past in class 7 and 8 about adding fractions. Let's try to add 123 and 45 100ths and 234 and 12 100ths, the fractional equivalent of the decimals in the first line. We can change the order of addition so that we're adding the whole numbers and then adding the fractions. When I do this, I find I have 357, and fortunately both of those fractions have the same denominator, so I can just add them. I have 357 and 57 100ths, or expressing that as a decimal, I have 357.57. What does that tell us? Suppose we just add these things up as if we were doing a normal addition and see what happens. I first line up the decimal points so that I have all the hundreds one over the other, the tens one over the other, the units, and then the tenths and hundredths line up. Then I just proceed as in normal addition. And I find that I get exactly the same thing as when I added them using the fractional equivalents. Let's look at some other examples. The first thing we do, as we did last time, was we line up the numbers we want to add, then we add them up. And in this particular case, you don't line them up exactly by number. What you need to line up are the decimal points, not the numbers themselves, because remember that to the right of any decimal part of a number, you can add zeros or not have zeros. The important thing to remember is when you say line them up, you're talking in this case if these numbers have decimal points to line up the decimal points. Let's take a look at that. Here is a fairly straightforward addition. Let's do it. 5 plus 2 is 7. 4 plus 1 is 5. Now that's where the decimal point is. 3 plus 4 is 7. 2 plus 3 is 5. And 1 plus 2 in the hundreds place is 3. So our answer for this is 357.57. Let's play some games now and remember where this came from. Again, I have 123.67 plus 234.45, and I'm going to change the decimal parts into their fractional equivalents, change the order, and then add these. When I add them, it's easy enough to add the whole parts. 123 added to 234 is 357. Good enough. Now I'm going to do the same thing to the fractional parts. And when I do, I see I get 112 100ths. That, if you remember the previous classes, is an improper fraction. And we can simplify that by dividing that fraction into the parts that are greater than 1 and the fractional part. Let's do that. I see that I can write that improper fraction as with a numerator of 100 plus 12 over 100. Well, the 100 over the 100 is just 1, so the equivalent of that improper fraction as a mixed number is 1 and 12 100ths. Now I can take that 1 and add it to the units part, to the 357 plus 1 to get 358. So that's 358 plus 12 100ths, and I'll bet you can guess what I'm going to do with the 12 100ths. I'm going to change that into its decimal equivalent so that when I add numbers where the decimal parts are greater than 1, I can then, what effectively is for addition, carry that into the whole number part of my numeric expression. And we see that it works if we start from basic principles in terms of the way that decimals are equivalent to fractions and performing the same operation on fractions, or on decimals. Let's just add this and see. 7 plus 5. We first put the decimal point in. 7 plus 5 are 12, so we carry the 1. 6 plus 4 are 10, and 1 is 11, but now we carry the 1 because it's greater than 1. We're in the 10th place, and we have more than 10 tenths. We carry it to the units, add that. 1 plus 3 is 4, plus 4 is 8, 2 plus 3 is 5, and 1 plus 2 is 3. So, to add numbers with decimals, the first thing we do is line up the decimal points, because it's important, knowing that you can have different numbers of decimals to the right of the decimal point. We line up on the decimal points, and then we treat it exactly as we would whole number addition. Let's look at some more examples. We'd like to add 58.123 to 12.98. And in this case, you notice that we have different numbers of digits to the right of the decimal point. What are the things we do? The first thing we do is line up the numbers at the decimal point, and then we remember that if we don't have the same number of digits in the two things that we're adding, we can always add a 0 on the extreme right-hand side of our numeric expression without changing its value. And now it looks like we have something that we can add up without a lot of trouble. 3 plus 0, I can do that. 3 plus 0 is 3. 2 plus 8 is 10, and I get to carry a 1. 9 plus 2 is 11, and I get to carry another 1. 8 plus 2 is 10, one more is 11. I carry that one, and finally I have a 7. So adding those two numbers gives me the sum of 71.103, or if I want to be entirely formal about it, 71 and 103 thousandths. Let's look at another example. 124 and 3 100ths plus 31. That can look a little bit confusing too, because there's a number with a decimal in it and there's a whole number. What shall we do? Just as I can put zeros to the right of any decimal I might have, I can also put in a decimal point with zeros after it without changing the value. Now I have something I can add together in the traditional way. I can line them up along the decimal point, and then I can just do the addition. In this case, it's reasonably straightforward. Put the decimal point down in the sum, then add them. And because it's a simple addition, I won't bore you with going through all of the addition. You can certainly pretty much by this time see how to do this just by observation. Let's look at another example. Here is, I'm not deliberately trying to confuse you, I'm just trying to cover all of the bases here. Here is 569 1/10 plus 0.0123 123 tenths, hundredths, thousandths, 10,000ths. 123 10,000ths to be exactly correct about this. In order to make this work, I notice that I first of all can stick a 0 in front of the decimal point. Putting numbers to the left, 0 to the left doesn't hurt. Then I can line up the decimal points, but I see I have a problem here. But I can fix this by adding zeros to the right of that 1, so that then I can do this very straightforward addition, put in the decimal point where in the sum where I need it to go. And this is important. If you forget to put the decimal point in, your answer is not correct. Then, of course, I can just do the addition as you would normally do an addition, and there's the result. Whenever you have something that doesn't look like it's going to work together, remember that after you line up those decimal points, it's always easy to add zeros to the right, and you don't change that value. Here's another interesting one. 8 plus 7.01010101. Let's try to sort that out. First of all, we see that we have 1, 2, 3, 4, 5, 6 places in that term with the 7. So we put in 6 decimal places in the 8 term. And with the decimal point, 8.000000 is numerically equivalent to 8. Then we line up the values underneath that, and then we do the addition. And again, I apologize a little bit here because it turns out zeros are fatter than ones, and so it doesn't exactly line up, but it's such an easy problem, I'm sure you can see how it might work out this way. What about subtraction? Let's take a close look at that. And amazingly enough, we're going to find that it's fairly similar to addition. Let's look. Again, we're going to do the same thing that we did with addition in terms of sneaking up on the procedures by using fractions or decimals that we already know about. So we see that the decimal 9.82 can be written equivalently as 9 plus 82 100ths. And we subtract from that the quantity. We have to be careful here. It's the quantity 3 plus 11 100ths. Now we simplify that. We know that when we have minus something in brackets, we've seen that we need to take the opposite of each of the terms inside the brackets. When we do that, the plus 3 becomes a minus 3. The plus 11 100ths becomes minus 11 100ths. Now we separate the integers from the fractions and perform the mathematics. Remember that since we have the same denominator, 100, in each of these cases, in the case of each of these fractions, it's going to be relatively easy to perform that subtraction. 9 minus 3 is 6. 82 100ths minus 11 100ths is 71 100ths. Now we can transform this directly into a decimal. And the result of that subtraction is 6.71. Let's take a close look at the procedure that we've used for doing that. There's what we've just done with the development using fractions. Let's just try this as a standard subtraction and see what happens. Like I did in addition, I line up those decimal points and I try to perform the subtraction. 2 minus 1 is 1, good. 8 minus 1 is 7, got that. Put in the decimal point. 9 minus 3 is 6. Just like addition, we line up the decimal points and then we subtract just like we've subtracted for whole numbers. Of course, we're going to look at another example, 13.75 minus 2 and 873 1/1000ths to say this correctly. We line up the decimal points, and I see I'm short a digit on the number I'm be subtracting from, so remember that we can always add a 0 there. And now I can do the subtraction, and I have to be careful here because if I perform this like a subtraction, I see I need to at least borrow a 10 from that place to the left. 10 minus 3 is 7. Since I've borrowed 1, I have a 14 minus 7 is 7. I've borrowed 1 from the 7 to feed the 14, so then I get 6 minus 8 is 8. I've now borrowed 1. I need to hit the 3, so 2 minus 2 is 0. And finally, I have 1. I've done this exactly the way I've done a regular subtraction, except that, again, like I've done with addition, I've lined up the decimal points and I've done it as I would an ordinary subtraction. Let's look at another example. $62 minus $48.75. Now, cents means 100. So that really what you're saying is 48 and 75 hundredths of a dollar. Let's do this subtraction. I put in $62 and no cents, and I can just do this subtraction as we've done it before. 10 minus 5 is 5. Borrowed the 1 from that, so 9 minus 7 is 2. Borrowed the 1 from the 2, so 11 minus 8 is 3. I've borrowed 1, so 5 minus 4 is 1. And I have to remember to put in that dollar sign, and the result is $13.25. Now we can look at adding and subtracting signed numbers with decimals, and it works just the same way as it worked with integers. We obey the same rules. If we think about this on the number line, I can talk about minus 8.023. How do I represent that? I go 8 units to the left, but because I have the 0.023, it's 23 1/1000ths. That's not much, but it's a little past minus 8. Plus 6.5, and I see that the result is going to be somewhere in the neighborhood of 1.5, again, because that 0.023 isn't too much. Let's actually do the math. But we remember when the signs are different, we take the absolute values and take the we subtract the absolute value of the smaller from the absolute value of the larger, and then the sign is the sign of whatever the larger of the two absolute values are. Let's see how that works. Here's our problem to start with. So I write the 8.023, or again, that's the absolute value. I'm ignoring that negative sign. I take away the smaller of the absolute values, 6.5. Notice I've stuck a couple of zeros to the right again to make it come out. I do that subtraction. And then the sign that I need to use when I'm finally done is the sign of the larger of those two numbers. I've taken the absolute value, but now when I finally tell you the answer to this, the sign needs to be the sign of the larger number. So when I've done this problem on the number line, I wind up with, because minus 8 is greater than plus 6.5, I go further to the left than I do to the right on the number line, so I wind up with a result of minus 1.523. What about when the signs are the same? We go, first of all, 4.8, almost 5 to the left on the number line, then another additional 10.2. We're going to wind up somewhere around 15. When the signs are the same, we just add the absolute value and keep the sign that we started with. So let's add these. And you can probably do this. There's a little carrying involved, but the point is that I keep the sign. So in this case, since I've gone only to the left, where I wind up is minus 15.071. It obeys exactly the same rules. Let's look at one more. I have 0.01824 minus 0.0097. In this case, I line up the decimal points. I need to stick in another 0 in the second term that I'm subtracting to make the number of decimal places equivalent, and then I just do the subtraction as if it were a normal subtraction. And the answer is 854 hundred-thousandths, if I wanted to say it correctly. And of course, just as we did with whole numbers, we can take the result of our subtraction, add it to the number that we subtracted, and it should come out to the number we've started with if the subtraction is correct. Let's look at another case. This is interesting. It's plus 0.0037 minus 1. Again, we subtract the smaller of the values from the larger, and in this case, again, we're going to need to continue to 10 minus 7 is 3, 9 minus 3 is 6, 9 minus 0 is 9, 9 minus 0 is 9, because we've continuously been borrowing from the digit to the left. Then 0 minus 0 is 0, and since the 1 is larger than the 0037, the sign is the sign of the larger absolute value, so our result is minus 0.9963.